supporter of this conference. I think you were here in 2008, even earlier than that, and was to be here in 2020, but of course that was a mess. Anyway, a very distinguished publication record, but I just want to, there's one great paper that everyone should read, very recent, Theories of Consciousness and a Life Worth Living. And today he will speak on consciousness is not something else.
Thank you. Does everybody hear me okay? Oh, there we go. Thanks. Thank you for coming out at like 8:30. You know who your real friends are, right? Here you are, all right. So I'm going to talk a bit about theories of consciousness and end with talking a bit about some data that I think goes in the direction that the field needs to go to get around some of the points of contention, right, that we've been having, where there's been not much consensus in this field, and yet there's an overabundance, I would say, of theories. I do want to thank the organizers, Stuart, Abby, and everybody. This conference is like a well-oiled machine. It's been going for so many years. It's terrific. I first came to this conference, I think it was in 1996, and that was I just was curious, and that was my first exposure to the science of consciousness or the neuroscience of consciousness, and I can honestly say that's probably the reason that I am here. Like the reason that I went into this area, this field of research, because I then went and got a PhD and started to do research. So thanks. So I want to start just by offering my talk in memory of Daniel Dennett and Daniel Kahneman. So two great minds that we lost recently. I think whether you agree or disagree with whatever they happen to dish up, I think we can all agree on the enormous contribution they've both made to modern thought. So, okay, so into the talk. So I want to start with just a couple of guiding principles. This is what I think in the morning when I get up in the morning. I think, how am I going to attack this problem again today? The first one is humility. We haven't cracked, consciousness is a tough nut to crack. We haven't cracked it yet. And who knows, we might be knocking at the door, we might be 100 or 1,000 years away. We don't know. But at the same time, I think you need to have a certain amount of authority and confidence, especially regarding what you don't know, right? I know that we don't know. There are certain things that we don't know. But also regarding some of the things that are pretty well established and that we can safely say, yeah, I know that, right? And then just a bit of meta-science, since I'll be talking about theories a bit. What makes a good theory, or law for that matter, or account? I would say that it's an account that is plausible, or at least possible, and it deserves to be tested and possibly ruled out. That's it. And so how do you measure success of a theory or law, right? First thought is, well, if it turns out to be true. In my opinion, no. No, just see above. If you've offered a plausible explanation that deserves to be tested, you've already succeeded. You did your job, right? Whether or not it turns out to be true. What are theories and laws meant for? They're meant to be challenged, okay? Tested, poked, prodded, and hammered from every angle. Right? Confirmatory evidence is good, we need it, but confirmatory evidence alone can only get us so far, right? Our job is to test theories, not defend them. This is the difference between my theory and a theory that I proposed. Okay. So now about consciousness. If I were to offer this to you as a model of you, say there's input, There's processing, and that processing can be reflexive, and it can be really complicated as you want it to be, and then there's output, there's behavior, right? Most people would say, well, there's something missing from that account. It's almost insulting, right? That's a garage door opener, right? There's this other thing. There's something else, right? There's what it feels like, or what it is like, the experience of processing that input and making decisions based on it, right? One of the cardinal examples that's often given is pain, right? So you touch a painful stimulus. You touched a point, you get poked by a nail. What do you want to do? Withdraw, good idea. Protect the injury, if there is one, another good idea. And learn something. Don't do that again. Right? That pretty much covers it from a survival point of view. And yet, there's clearly something missing. It hurts. Right? There's pain. Well, what's that? So that's, at least when we think about and talk about consciousness, and very often it's in those terms. It's like this something else. Right? And that something else is really difficult to operationalize and isolate. These are some sort of canonical cases where we've tried to come close, right? Blind sight, sleepwalking, coma and disorders of consciousness, dreamless versus dreaming sleep, which is probably closer than all the others, right? But all of these are problematic because they don't really isolate consciousness. Blind sight subjects can't do just anything, right? They have a very limited repertoire of behaviors that they can do by guessing. And for example, in the case of coma and disorders of consciousness, when you lose consciousness due to a brain injury, you lose a lot of other things as well, right? You don't become a philosopher's zombie when you lose consciousness due to a brain injury. If you did, it would be a perfect case for studying, but that's not the case, right? So these are all problematic. The real difficulty with the something else formulation is the measurement problem. I can measure input, I can measure brain activity, I can measure your behavior, and I can measure things like skin conductance, your heart rate, breathing, pupil diameter, all these, I can measure all those things. But this cloud thing, I can't put an electrode in that, especially when you define it from the get-go as something else. So one possibility is, well, yeah, but you can still measure it indirectly. You can ask people about their experiences, which are private to them, and they can tell you about them. It's sort of like the Higgs boson, where, or in general, when we do these experiments in particle accelerators, you don't see the particle itself, but you see the traces it leaves in some kind of medium, right? But the analogy doesn't work, because in physics, for example, in the case of the Higgs boson, you need that Higgs boson in order to fill a hole in your theory. You need it. Otherwise, the theory doesn't work, right? You need to, so it was predicted back in the 60s. This thing ought to exist. If it doesn't, all this math doesn't add up, right? In the case of consciousness, you don't really need something else, right? When you're talking about the observable facts, right? I can account for all the things that someone says and does, in theory at least, by looking at their brain activity. I don't need to invoke something else. And that's the essence of Occam's razor, right? Which I think came up in one of the talks yesterday. In a nutshell, right, Occam's razor is keep it simple. Don't invoke more descriptive or explanatory stuff than is needed. So, for example, where do babies come from? Well, mating, sperm meets egg, gestation, etc. That covers it. Plus pixie dust, right? Oh, wait, right? You don't need the pixie dust. You're done. Stop. Right? That's Occam's razor. And I think I'll come back to that towards the end. when I talk a bit about illusionism. So a big part of the problem is just defining consciousness in the first place. What is it? We don't even all agree on that. One thing I'll say is that very often, science doesn't start with definitions, right? We start with observations, and then we try to work toward forming a definition. And in a way, that's kind of what we're doing now, right? And that argues that we don't really need more theories. We need more data, and not just data, but the right kind of data. So, but what is consciousness? Well, very often we talk about it in terms of what it's not, right? And here's sort of a laundry list. Okay, so neural information processing. It's not that, or at least it's not just that. If it were, we wouldn't need a theory of consciousness. We just have a theory of neural information processing, and we're done. What about things like grouping and segregation? Well, again, you don't need to invoke consciousness to explain grouping and segregation, or even object representation, or even metacognition, right? And by the way, these bottom three all sort of fall into the rubric of perception. Again, if perception were identical to consciousness, we wouldn't, again, need a theory of consciousness. We would just form a theory of perception and we'd be done, right? So it has to be different from these things. This is what I think consciousness can be operationalized as fairly. It's the process by which neural information becomes subjectively experienced. So if you imagine a space of all the possible things, all the possible kinds of information that a brain could represent, all the kinds of inferences that a brain could entertain, right? That's this space shown by the blue arrows there on that plane. Then there's this orthogonal line, right, that defines the process by which whatever that information is, whatever those representations are, the process by which they become subjectively experienced or associated with a subjective experience, right? And that's what we're after. So if you sit in this space of contents, you'll be missing the point. Now, some say, oh, well, okay, you still can introspect. We still have introspection, right? We can directly tap into this something else, each of us ourselves, through introspection. Well, that's problematic too. Here's a quote from Thomas Metzinger: introspection, just another kind of processing, right? It can access the information content of consciousness, but not consciousness itself, right? It can access this plane here, but not that orthogonal line. And, as an aside, right, if you do want to go at it through introspection, then you had better not tell anyone about it. Because as soon as you do, or press a button or do anything, right, as soon as you do, it becomes behavior, or at least it becomes confounded with behavior. So I'm going to introduce the challenge with this, something else, through a little story, a Faustian bargain, right? So imagine that you're offered anything you want, fancy cars, a yacht, a really buff body, access to a great chef who cooks you amazing food, whatever you want, right? But you're not asked to bargain your soul, right? You're just asked to bargain your subjective experience, your consciousness. You're asked to bargain away the something else. So now, bargaining with the devil sounds a little unsavory, so you can think of it as bargaining with a friendly philosopher who's being really upfront about what you're going to give up, right? And the philosopher adds, well, but once you've given up this something else, it won't change anything about your behavior, right? You'll still say, that tastes good when you eat some good food, and you'll say, isn't life amazing when you're cruising on your yacht, right? And if someone asks you, are you conscious? You'll say, sure, I'm conscious, right? It won't change your behavior one iota. So what you will have given up is something that no one, not even you, will ever know that you've lost. And so the question is, well, would you take the bargain? Now, many of you will recognize this as just the hard problem of consciousness, right, in another guise. But this bargain kind of, depending on whether you would accept it or not, kind of separates people into two camps, where you either feel like, hey, if I give that up, I've literally given up everything. And the other camp is, well, if I give that up, I've actually cheated the devil because I've given up, or the philosopher, I've given up nothing at all. Right? So there is this hard problem, this chasm, and we're all, I think, in this room familiar with it. The modern era of consciousness research has been defined by the neural correlates of consciousness workaround. Right? Set aside the hard problem for now. Let philosophers think about it. We can still debate it. We can set it aside. Just try to narrow in on what's going on in the brain that is correlated with consciousness. And it's definitely been a productive workaround for empirical research. But I'm going to argue that it's problematic for theories that grew up in this context. What tends to happen, and pretty much every theory I know is guilty of this, is what I call the big bait and switch. So at the outset, at the beginning of a paper or a talk, the theorist declares subjective experience to be the explanatory target. They talk about the redness of red, the smell of a rose, all those things, phenomenology, right? That's how they introduce the topic. Then they propose an account of what goes on in the brain when there is or is not a subjective experience, and how that's accounted for by their account or their theory. So, i.e., neural correlates, right? And then, towards the end, they throw in a disclaimer, right? Of course, we don't claim to have solved the hard problem, right? That would be crazy, right? We haven't done that. I would argue that such accounts, and this really is basically most theories, they're descriptive. They're not explanatory, by their own admission, right? And thus, they are not really theories, because theories are meant to explain things, right? Have to address the question of why. That's why we call Newton's law a law and not a theory, right? Newton gave us this equation. He said, this is the way gravity works, right? I can make predictions. I can test those predictions. But I'm not explaining why. I'm just describing. Right? I'm describing how gravity works, right? It's why we call Einstein's theory a theory, right? Because he actually explained why. Gravity is a warping of space-time. Now, of course, that gets explained in terms of other things that then themselves need to be explained. But okay, but you've pushed it one step further. But you still have explained something, right? So I've argued that what we call theories are not really theories. They're laws, or they're competing laws. Some of them might be right, some might be wrong. And since we have this sort of overabundance of theories in this field, I think we need to be especially mindful of how do we evaluate them. We need to set up some criteria, right, by which to evaluate their fitness and adjudicate between them. Right? There are the sort of more general challenges. Is it testable? Can it be disproven? Is it parsimonious? Some theories fail miserably on this one. And then specific to consciousness. And these are some that I've proposed with my co-authors, Adrian Durig and Michael Herzog. Does it address the sort of paradigm cases of consciousness? Right? Like binocular rivalry and waking up in the morning and things like that. Does it offer an unconscious alternative, right? Again, if for any given brain event that's conscious, there's no alternative to that brain event that is processing similar information but isn't conscious, then there can't be a science of consciousness, right? It's just a science of neural information processing in the brain, right? Perception and consciousness would be the same thing, and we could just talk about perception. Can it be realized in a suspiciously small network? At least for some of us, that's a problem. Can it be realized in different substrates? Right? Problems with most theories, in my mind, all modern theories of consciousness have their issues, all of them. Right? Roughly none of them addresses the hard problem. As I just said, they're descriptive and not explanatory. Typically, a leap of faith is required. You get to, here are the conditions that I assert are necessary and sufficient for consciousness, and then boom, you get it. You don't get that line that answers the question why, drawn between this brain phenomenon and subjective experience, right? And they tend to push you towards dualism or panpsychism, for example, in the example of IIT. One alternative that's become more popular recently is attention schema theory, which is an illusionist theory, right? According to attention schema theory, consciousness is a perceptual attribution or inference that we all make. And that inference arises from an internal model of selective attention that we apply to others and to ourselves in order to predict behavior. As a consequence, we come to believe that there's something else. We become convinced that there must be something else. Now, there is a problem, even with AST. According to David Chalmers, it does a good job of dealing with the meta problem of consciousness. That is why we believe we have consciousness, but maybe not phenomenology itself. Right? Maybe. So I think there are ways that AST can actually address phenomenology, the right here and now of subjective experience. Right? But I'll table that for now in the interest of talking more broadly about illusionism, because attention schema theory is just one possible illusionist theory. It could be wrong, even if illusionism as a framework is still on the mark. Right? So again, the illusionist stance is there really is nothing else. We don't need it. We don't even need to invoke it to explain the observable facts. Right? And a nice story, this has been offered by Mike Graziano. This is actual, real anecdote. There's a patient, a neurology patient, who I presume had a stroke, and is talking to his neurologist and says, you know, I have a squirrel in my head. And the neurologist says, okay, well, I mean, I guess you mean that you have like the thought of a squirrel in your head and you just can't get it out of your head, like when you have a tune, you know, in your head and you just can't get it out. No. The patient says, no. I have an actual like furry animal living inside my cranium. Like, totally. And the neurologist says, well, I hope you can appreciate that that just doesn't make much sense. It's not possible. Plus, we have your brain scans. I mean, we would have seen the squirrel. The patient says, you know, yeah, I know, I agree. But then he goes on to note that logic and physics cannot account for everything in the universe. So, and he's back to square one. Look, sorry, I know that sounds impossible, but I definitely have a squirrel in my head. Right? Question. If you were a scientist working with this patient, what would you seek to understand in this case? Would you, A, apply for a grant to search for the squirrel? B, apply for a grant to figure out why someone might believe she has a squirrel in her head? Or C, not apply for a grant because it's really freaking stressful. I think B and C are both reasonable. A, I'm really doubtful of. Well, this is really a metaphor for what we might be doing in the science of consciousness. We might be hunting for this squirrel that we all think we have in our heads. Right? And according to AST, we come to believe and be convinced and have a strong conviction that we have this something else in our head because we have an attention schema. So again, Occam's razor, keep it simple. Don't invoke more descriptive or explanatory stuff than is needed. So, if I can explain all the things that people report about consciousness in terms of brain activity, am I done? Is there anything else that I need to invoke? Right? In my mind, the answer is no. No pixie dust is needed. Okay, so people say, oh, so consciousness is a shared delusion. That's just ridiculous. Well, not quite. First of all, not everyone shares it. Like, I tried to explain all this to my grandmother. No hard problem for her, right? I'm conscious. It's all good. Have a bowl of spaghetti. I mean, it's important to realize, right, the number of people in the world that are afflicted with the hard problem is vanishingly small compared to the global population, right? But also, it's not like the squirrel. The squirrel really is just a useless delusion. According to AST, that quote-unquote delusion is it's a story about something real. It's about selective attention, and it has a function. It helps us stabilize attention, and it helps us predict the behavior of others and ourselves. So, back to what makes a good theory, a good account. Is illusionism a worthy idea? Is it plausible, or at least possible, and does it deserve to be considered and possibly ruled out? I would say absolutely, right? And again, note that any given illusionist theory could be wrong, even if illusionism as an approach is still on the mark. Okay, so if we start here, though, then is there anything meaningful left to study? And if so, how should we go about defining consciousness? Well, I definitely think there is. Among other things, consciousness is characterized by a neurobehavioral dissociation. There are things you can do without consciousness. There are behaviors that are possible without consciousness of the relevant stimuli, the relevant information. And then there are all these other behaviors that are possible. Anecdotes often center around driving. I can drive and make all these turns and avoid obstacles, and then suddenly I forget, I'm not sure I was ever conscious of any of it. I was just on autopilot, right? So we can work to draw that boundary, push the limits of what you can do without consciousness and just see how far you can possibly go. Because the better job you do of defining that boundary, the more precisely you'll be able to narrow in on what is going on in the brain that belongs to one side or the other, right? Which is what we're trying to do. And possibly a lot of the sort of competing accounts that we get empirically, from research, may come from just not having a very clear idea of where that boundary is. Because you have to use it. When you do an experiment, a neural correlates of consciousness experiment, you have to take your data and separate it into the ones that were presumably conscious and the ones that presumably weren't, and compare them. So how you draw that line is paramount. Another thing I think we might consider, and this, a lot of people don't like this, but is to just drop the word consciousness altogether. Partly not because it doesn't point in the right direction, but because it has so much baggage and means so many things and is so imprecise. Maybe Danny Kahneman had it right in not overspecifying something that we don't fully understand. He just talked about system 1 and system 2. And system 1 are all the things that we could sort of do automatically, implicitly, without reflection, not deliberately. It likes probabilities. Whereas system 2 is what would map onto what we what we here talk about as consciousness, right? And system 2 likes certainty. I would add that system 2 operates in a regime where false positives are costly. And I'm going to show you some research on that. And that points, in my mind, to it being important in the domain of proactive decision-making, where, by the way, the allocation of attention is important. All right, so this, in a gist, is what I think is one of, at least, the big questions we can still chase after, whether you commit to illusionism or any other theory, right? The boundary of non-conscious processing. And my first best guess is that consciousness knows when. That is, you can't initiate a new movement in response to a stimulus without being conscious of it, right? And when, knowing when, which that implies, further implies that there must be a threshold. This idea came to me when I was studying blindsight. Because if you put a stimulus in the patient's blind hemifield, or if you ask the patient, okay, just wait, and when the stimulus that you can't see appears, raise your hand. Well, the patient will never raise his hand, right? Imagine if I set you in front of a display and said, when the stimulus appears that you can't see, raise your hand. I mean, you could potentially do this and say, oh shit, why did I just raise my, I don't know. That just doesn't happen, or it's what I'm arguing. You could prove me wrong, right? But that I think is getting close to where that boundary is. One way to map it is along the usual psychophysical curve, where I just measure your performance on a task, going from a very weak signal to a much stronger signal. We get this kind of curve in psychophysics. The question is, where does the threshold of consciousness land, or the threshold for system 2 land on there? Some argue that there is no separate threshold. That's it. This is the threshold, right? I tend to think that there's a separate threshold for subjective experience. Right? And I've been looking at that using a few different techniques, backwards masking being one of them, also color fusion, which is a technique that I've worked with for a number of years, where if you show these two color stimuli with opposing foreground and background, if you show them dichotically, so separate to each eye, when you fuse them, the colors blend cortically, and you just see yellow. And you can vary the color contrast, and at certain color contrasts it becomes visible, and at lower contrasts it becomes invisible. So what we've done is applied a simple rule. If there is a threshold for what it's like, if you will, then if I ask you the question, if I show you two stimuli, two versions of the same stimulus at two different levels of intensity, and I ask you, did they look the same or different? Well, the probability that you're going to say they look different ought to be maximal when those straddle the threshold, right? If there is such a threshold. And the probability should be lower when they're both below and when they're both above. So what does this predict? Well, first of all, if the threshold for consciousness is graded, like in the upper right, then we predict a function of the probability that you'll say they look different, depending on the stimulus intensity. That should be flat, no peak. But if the threshold is relatively steep, then you should get a peak in that function. So here's data from a bunch of subjects. A couple had it missing. And you can see there are a lot of peaks there, right? And on average, so this is this function is the probability that the subject will say they look different as a function of the stimulus intensity. So on average, that function has a nice peak. Well, what's nice about that, right, is that effectively what we're measuring here, right, this peak, is kind of like a derivative first derivative of their threshold function. So we can just take the integral and look at where that aligns with not only with this traditional psychophysical curve, but with all the other traditional measures that we use to measure conscious perception experiments, right? And what we're finding is that subjective threshold, the threshold you get defined based on this task, based on this simple rule, is higher and much steeper than the threshold you get by looking just at objective task performance, right? And all depended on how we asked the question, right? Because targeting subjective experience, getting people to answer a question, what did it look like to you, is not as easy as it sounds, right? I remember when I was doing my PhD, dozens and dozens and dozens of Princeton undergraduates, they kept trying to tell me what was on the screen, not what they saw, right? Because they presumably didn't want to admit that they didn't know something. So, and again, this points to what I mentioned before, that conscious perception seems to operate in a domain where there's an aversion to false positives. So I think that this is a fruitful avenue. There are many others, but it's just to say that we're not left with nothing if we take the illusionist stance. There are many questions about consciousness that are still worth asking. I'm going to stop there. I don't know if I've gone over time. I just want to put in a plug for a new book that'll be coming out in the fall that I'm co-authoring with my colleagues Michael Herzog and Adrian Dorig. It's called The Neuroscientific Theories of Consciousness, the Grand Tour. Again, it's due out in the fall. Thank you very much for your attention.
We can take a couple of questions. I'll start over there, please.
Okay. Thank you for your talk.
Mm-hmm.
Thank you for the opportunity of coming up here. I would like to ask a question and also propose an answer. The question is it possible to have a standard model of consciousness? We have many models. Is it possible to have a base model from which we can refer the other models to? And what I would like to propose is that, yes, there is possibly a standard model, and here it is. Okay, I have it here, which I will give it to you, and anybody who's interested can come and get a copy from me. Now, how do we know that this is a possible standard model? First of all, we test it. Test it with people, and in the audience here, in this meeting here, I've tested it with 10 people that came up to me. Volunteers, I never met them before. And we had 100% positive result. They can understand this, right? So we got 100% agreement that this can be a standard model.
Well,
but that is not enough. We have to have a standard model that is simple. Is it simple enough to be on just 2 pages like this? And we need a Turing test. The Turing test is, can a 10-year-old understand this? If a 10-year-old can understand this, it passes the Turing test.
So let me, because I know you're offering an answer to the question, but I suppose you also would like to perhaps hear my answer to the question. Not to be vain, but I think it is possible in theory. Coming up with a standard model of consciousness is possible in theory, but insofar as it depends on people agreeing with each other, well, you know, in actual fact, it may be hard to get there.
Well, I'm saying is, don't believe me, okay? Go for a test drive. And yesterday, we went for a test drive with a young person last Tuesday morning. The speaker brought his son up on stage. We tested out with his son.
I'm sorry, this is not a question.
So I'm
this is
ending
a
here
disquisition.
now. I'm finished now. I'm just going to present you with a model.
Okay, one more brief question, please, from this side.
Sure. I mean,
First of all, thank you
Thanks for
for
your
your
question.
talk this
Thank
morning. I found it very illuminating. And I'd like to ask you your opinion on the theory that says that consciousness is a field that we inhabit that presents itself as two separate items, but in fact are one. And in all deference to the adage, the word is not the thing, the two ways it presents are what we interpret as emotion and what we interpret as mentation or thought.
Okay, I'm not sure I understand the question.
Consciousness is a field that we inhabit, and that the two parts that we recognize that it is are emotions and thought. We interpose our ego in the middle and say they're my thoughts or my emotions, but in reality it is us apprehending the field itself.
So, I mean, are you asking if I agree?
I'm asking your opinion.
Yeah, my opinion. I mean, I guess you just heard it. I think that consciousness is a perceptual inference. It's an attribution that we make, and we attribute it to ourselves, we attribute it to others. It's an outcome of perception. So I guess, I mean, I'm not sure what you mean by a field, but at first blush, I'm not sure I agree.
Well, like a Higgs field, we inhabit this field around us that we've not been aware of in its totality. We never even thought that a field could exist other than the one we acknowledge as a three-dimensional reality. It's not seen, but it's felt, and we interpret it as emotion and thought.
I guess, I mean, I'm not sure that I agree, but I'm happy to chat offline.
Okay, we should stop there and thank our speaker. Our next speaker is Pieter-Jan Maes from the University of Ghent. He works in something I didn't even know existed until recently, systematic musicology, with special reference to embodied and social interaction with music. Lots of interesting stuff. And he'll speak today on music and XR influence. Thank you.
So thank you. Can everyone hear me? All right, yes? All right, thank you for the introduction. I also would like to thank Stuart and his team for a wonderful conference. It's really great to be here. I also want to thank you all for attending the talk. So the question that will bind my talk today is the following one. How can music and extended reality, so extended reality taken as an umbrella term for virtual, augmented, and mixed reality, so how can music and XR influence the human mind and behavior, specifically when used as a biofeedback system? So this is a mouthful. It sounds quite technological in scope, but essentially the research that I will present really relies on the quality of music itself and how we interact with music. So even in its most basic forms, music can have a profound impact on the human mind and behavior. And to show that, I would like to start with a little video illustrating my point. I take you to West Tanzania, where music is naturally integrated into daily life activities of people and the community there, specifically in a farming context. So let's have a look and a listen first to this little video. All right, so you could ask, what is the function of music here? Why don't they just work in silence? So people here seems to be naturally attracted using music. So why is that? And there has been done research on the reason why music is used in this context, specifically by researcher Frank Gunderson, who did research in the context of sucumulant farming. And he conducted interviews with these people. And what came out systematically is that music is used for motivation, for perseverance, for distraction. So you can read these quotes, without the music, you just get tired. You just go on farming, forgetting your worries. The person will not feel the weight of his hoe anymore. So apparently, if you combine music with physical effort, with physical activities, these activities become more pleasant. So that's a real power of music, I would say, that you can really alter the experience by adding music to this context. And so definitely a first effect of music is to alter the subjective experience, both for an individual and for a social group. We also have a group identity that is built through the practice of music. But a second effect, an important effect also, is how music can help coordination of movement. If we looked at the video, on the left you see the fiddle player, and the fiddle player sets the pace for the other workers to work, right? So it's a kind of temporal framework to coordinate actions. At the hose there are bells attached, so people can, by chopping, by working, they can follow the fiddle. But it's not only following, they are really forced to follow. Imagine if someone is a bit lazy and decides to work a little bit more slowly, what would happen is you would disturb the musical result. This person would be detected immediately as being lazy, right? And so music is a quite interesting strategy to force people to behave in a specific way, and so to drag people along in one rhythm. So coordination here, another function of music. And now, instead of talking about music, I would prefer to speak about sonification and musical biofeedback to emphasize the connection to body movement. So if you consider a musical instrument, from very simple instruments like bells attached to a hoe, to a grand piano, a more advanced instrument, basically what instruments do is to transfer actions and patterns and qualities of these actions into corresponding patterns and qualities of the sound, and this sound is then getting back to the musician, the person. So rooted in action, you create what I would call a sonic universe, right? A sonic universe that aligns and integrates an action perception loop. And this loop, this sonic universe, has the potential to alter what we feel and what we do, right? And also to study in more detail the human mind and behavior. And so that's what we do in our group, and I would like to show you one of the older studies done by colleague Tom Fritz, who is working now also at Max Planck Institute. And so he studied a context which is at the same time different but also similar to the sucumulant farming context. He developed a concept, jimin. It's a compound concept, both referring to gymming, so having a physical workout, and jamming, so musical improvisation. So again, a combination of music expression, and physical exertion. And basically what gymming is doing is creating fitness machines as music controllers. And so this is an example. So a tower, for those who go to the gym regularly, a familiar fitness machine. So you have to pull weights. And so you can see by operating these machines, by putting effort in it, this is translated into corresponding sounds. Under the hood, it's actually quite simple. The weightlifting is transferred to a slider going up and down, and with this signal you could manipulate musical parameters like amplitude and filtering. So I would like to point out again the similarity with Sukumuland. So we have the sonification scheme there. You do something, you create a corresponding sound, and you give that back to the person. Now here, a difference is that you extend this action perception loop into the digital, right? And therefore you need some technologies like bodily interfaces to get the action into this digital realm of sound, and to get the sound out again you need also some basic technologies like headphones and speakers. And so together with the team we created multiple of these fitness machines, and yeah, then we end up with something like this. So Tom is the person to the right. So this is fun, but of course we are interested in the science, and so Tom came up with an experiment, a fairly simple experiment. The task was to gym in a way that is comfortable for the subject. So they came in groups of 3, and they had to gym in 2 conditions. One condition was a passive listening condition, so there was music, but the subjects did not have control over the sound, so it was passive listening, while in the second condition they could actively manipulate the music, as was shown in the videos. Now, while doing this, 3 measures of physical exertion were taken. The first measure was the delivered force. What is the work done throughout the trial? A second measure was oxygen consumption with specialized masks, giving an indication of the energy that was used by the muscles. And the third measure was a subjective rating of the feeling of effort, a feeling of exhaustion. And now looking very briefly at the results, so at the horizontal axis you see the measures, and each measure is expressed as the value measured in the passive conditions over the value in the active condition. So one means the value was the same in both conditions, and that was the case for the delivered force, the work that was done. So the same work was done both in the passive and the active condition. But interestingly, in the other 2 measures, the value was significantly higher than 1, meaning that in the active condition, less oxygen was used. So they did the same work, but with less energy, let's say. And the same we could say about the subjective rating of the feeling of exhaustion. So when actively manipulating the music, people felt less exhausted, which is quite remarkable, and we could reflect back this result to the Sukumuland farming. It gives an indication why people give or use music. It's to lower the feeling of exertion, to alter their subjective experience. And next to subjective experience, so we also did experiments on how music can alter motor coordination. And so we've done extensive research in this in the context of sports and motor rehabilitation. And so the D-jogger is the oldest application that generated quite a bit of research. And again, it's a compound concept. The D-jogger is older, but it's also referring to 2 concepts. One is jogging. So it's an application that it's meant for runners, for joggers. And DJ, the main occupation of a DJ is to align, to set the tempo. And that is exactly what the D-jogger is doing. It automatically aligns music to running cadence, right? So the beats of music are automatically aligned with the foot strikes. And for that we use coupled oscillator models, but it's not so important for now. Let's have a look what it exactly does. So this is a slow motion. So you see attached at the ankle there is an accelerometer. So we capture the action patterns in foot strikes, and we transfer that to corresponding patterns in the sound, the beat pattern, and we give that back to the runner. So again, we make, or we construct, we design a kind of sonic universe around the runner. Now the idea here was, can we use this application to alter motor coordination, specifically the running cadence? And so for that purpose, we did do an experiment, so a couple of experiments actually, but I will only briefly discuss one here. In this experiment, again, a very simple task. On a running track, runners had to run at a comfortable tempo, basically, right? But each trial was divided into three distinct phases. In the first phase, people had to run in silence, just normal running. In the second phase, people had to run, but we gave them the effect of the de-jogger. So the music was automatically synchronized to the running cadence. And so we saw this as a reward. So you have control over the music while running, and you get a certain agency over the music, and this gives you a pleasant feeling in stage 2, and then in stage 3, we take away this reward. So we speed up the music, or we slow down the music. So what happens if you speed up the music? This means that the beat will come just before the foot strike. If you slow down the music, the beat will fall just after the footfall. Now, what you do is you take away the reward, and let's imagine if you take a candy, or you give a candy to a child and then you take it away, what happens? The child is running after the candy. And we predicted that the same would happen here, and that you would look again and search for this alignment of your bodily rhythm and the musical rhythm. So meaning that when speeding up the music, we predicted that people would also speed up their running cadence, and vice versa when slowing down the music. Looking at the results, more or less the prediction came out. And so at the horizontal axis, you see the change of the musical tempo in phase 3. And so we had a series of different manipulations of slowing down from -3% to +3% speeding up. And so on the left, you could see the change that it affected in the running cadence, expressed as a percentage. And so here you see, without going into detail, that indeed, if you speed up the music, the running cadence will speed up accordingly, right? So by little manipulations in the sound, we could alter the bodily rhythm of the runner. Now, we did the same or a similar thing with another parameter in the running, foot strike impact. So it's an important feature. And a lot of runners, especially recreational runners, have too high of a foot impact. And so this increases the risk for injuries. And so it's good to have a system that can lower the impact if needed, right? And so we developed the low impact running application. And basically, again, it implements this sonification scheme that aligns the action perception loop. So here again, we use an accelerometer attached to the ankle. We measured the action. So in this case, it's what is called the tibial acceleration, so the impact of the foot strike. And then we looked based on a certain threshold. If the foot strike is below the threshold of an increased risk of injuries, then we rewarded, so to speak, the runner with pleasant consonant music. Now, on the other hand, if the acceleration, the impact is above this threshold, so there is a risk for injury, then we gradually added noise onto the sound signal. So a kind of punishment, so people would change their behavior. And so in an empirical study, a longitudinal study, a number of runners could use the system to regulate their impact, and the results were quite promising. So people could use this sonification system a biofeedback system to regulate their foot impact. Now, we did quite a few other studies and other contexts, but again, also always based on this idea of sonification. We had studies with stroke patients. In stroke patients, often you have balance problems, and so people, when they are standing up, they are a bit skew. And so with sonification, we also develop interventions to get them in balance again, also to avoid injuries and back issues and all that. We also worked on cycling, which is more or less similar to running. Breathing, we did as well. So we could use music to lower the respiration rate, so to bring people into a more relaxed state. We could also alter the respiration rate or the ratio between inhaling and exhaling. So this is an indication that you do not always have to use substances to get people into relaxation, but music can have a similar impact and can be used in a lot of interventions as well. And then the last one is weightlifting. There it's very important to have a straight back in order not to break the back when you lift the weights. And so again, we could use sonification to keep the posture correctly. All right, so up until now, I only talked about the sonic environment, so using sound. But at a point, I thought, would the same be possible with immersive audiovisual stimuli environments, right? And in essence, this is nothing new. As you can see on this slide, throughout history, across cultures, people somehow have always had the desire to construct immersive imaginary worlds, right? Specifically in the domain of the arts and in the domain of religion. And so the design of these imaginary worlds was always somehow there. Now, what is different is the technologies used to do this, to create these immersive worlds. And nowadays, we have a very interesting technology, the technology of extended reality, so virtual, augmented, and mixed reality. And so that's what we are currently also doing in the lab, trying to explore these technologies and to shape human experience, consciousness, if you want, and also motor coordination. And a crucial concept in this research is the concept of virtual embodiment. And there is a lot to say about this concept, but yeah, the time is a bit limited. But essentially what virtual embodiment is, you can imagine virtual embodiment as taking over the sensory motor system of a virtual avatar, right? A digital twin which is immersed in a computer-generated world. And by taking over the sensory motor system of an avatar, you can interact with a computer-generated world, very similar as to how we interact with our physical world. And it becomes even more interesting because you can also do other things. You can interact with the computer-generated world in ways that is not possible in our physical world. And then these technologies become very interesting also to do research on consciousness. But now, how do we take over the sensory motor system? Well, there are two components. First of all, you have the action component. And basically what it does is whatever a physical person, a real person is doing, the virtual avatar is mimicking, right? And so for that, you need motion capture technologies. And here you can see an example how we do it in the lab. So we start from a physical performance, in this case a dancer, which is equipped with a motion capture suit. Then we build it into a skeleton, and in the next step, we turn it into an avatar, mimicking exactly what the physical person is doing, but in a virtual environment. Now, this is only one part. there is also a very interesting set of technologies to take over the senses of your avatar. And the most well-known technology is the VR glasses, right? And basically what you do if you put on these VR glasses is you can look from the eyes of your avatar, right? And so in the immersive display, you get the image that the virtual avatar would get into this computer-generated world. So you move, your avatar is moving, the perceptual field is changing, and this field is projected into the immersive display. So let's assume this blue ball, you add this to the computer-generated world, and so this would be the perspective change if the avatar is moving. And so you can really walk around. And so essentially here is that you can experience this computer-generated world from the inside out, right? From a first-person perspective, from the perspective of your avatar. Now you have other displays as well. You have them for all the senses, basically. You have them for the auditory channel. You have the headphones or the speakers. There are also haptic devices, so you can literally feel through the skin of your avatar. There are also olfactory displays, so you can smell through the nose of your avatar. So for every sense, there is, in theory, in principle, a display. Now, it's not only about passive observation, so you can also interact. So here, it's an example that you take over the hands of your avatar and you can interact with objects in the computer-generated world. Here we simulated a sound studio from the 60s and the 70s. It's not so important. The idea is that you can interact with these objects. What is important, though, is an important concept, the concept of presence. So immersion is a concept that relates more to the technological realization of an immersive world. But presence is a feeling. It's a psychological feeling of actually being inside of a computer-generated environment. Of course, it's an illusionary feeling, but it's a very essential feeling related to extended reality technologies. Now you can interact with objects, but you can also interact with other humans. So I showed how you could bring one physical person into the virtual world, but you can do the same thing with two or multiple peoples at the same time. So imagine that people are in physically remote locations. You can bring them together into one virtual space where they can meet and interact with one another. This video shows how we do it in the lab in Ghent. So this is a colleague in one location, one lab, equipped with a motion capture suit. We go to another dislocated lab. There's another colleague also wearing a suit. And so both can be turned into avatars. And we can bring them into one shared virtual environment. And by adding visual display, auditory displays, they can also see from the eyes, hear from the ears of their own avatar in this space, and so see the other as an avatar, right? So now we investigate, okay, interaction through these avatars. And so basically, can we play music mediated by avatars? So we did a couple of studies in this area. On the left side, we had some case studies where we tested the concept in piano duets, right? And on the left was a larger sample study on a polyrhythmic music performance, right? If you're interested, you can read the articles that I referred below. But basically, results were positive, so people could play together, so they could play a score. It was also promising because they could also exchange cues with one another through their avatar. And the experience of the performance was also quite well. So for now, pretty promising results, I would say, although we are still at the start of this research. Now, in these experiments, so avatars are controlled by humans. We also use agents that are not controlled by humans, at least not in real time. Agents, as you see on the right, they are rooted in physical performances of real humans, like a drummer. We could turn into an agent, right? But they are not controlled in real time. And so what we test in the lab is, based on these agents, can we create holographic music performances, and we study these from the perspective of the audience. So based on quantitative, qualitative measures, what is the experience of audiences when engaged in holographic music concerts. We also tested in the domain of music instrument learning. So with agents, we can turn the teacher into an avatar, right? It's not to say that we exclude the teacher, not at all. It's an interaction between the physical teacher and the model. But here, this model is used to correct posture in students. So students can take it at home and use the model to learn more about correct posture when playing pieces of music. And this third window provides an example of an interactive agent. So these first two were more passive agents. In the right, we work with an interactive agent. And so what the agent is doing in this case is automatically aligning its performance with real-time human input. And so the human input is tapping, drum tapping, and the avatar automatically synchronizes with this input. So if you speed up the tapping, the stick on the hi-hat will always be in the same tempo. Under the hood of this is also coupled oscillator models, and actually it's fairly similar to our de-jogger system. The only difference is that we add a visual component. We add the visual representation of the agent. But for the rest, the coupled oscillator below is the same. Now, this is important for us because these agents provide us a new methodological tool to do research. So we are interested in joint rhythmic coordination. And so we observe and we study humans, so musical ensembles, and we model timing in these ensembles, specifically from the coupled oscillator perspective. But agents provide the opportunity to further test these models. So models that we obtain by human research, we can build into these agents and further refine and further test these models in human-agent interactions. So we can control timing, but basically we can control any kind of behavior of this agent. Also the appearance we can change. Now, in this case, it's a very neutral agent, but with the technologies available today, you can turn them into very realistic 3D agents. And now it gives us an optimal trade-off between realistic stimuli and experimental control. So for us, this is, on a methodological level, a very interesting technology. So this is an example. I will not go into too much detail, but here we controlled the musical role of the agents. So we were interested in leader-follower roles and how that it affects the feeling of social cohesion. And so is it changing when the avatar is only following or leading, right? And so in this case, we had three conditions. The subjects could only watch the agent. In the second condition, the agent was always doing its own thing, right? Keeping a constant tempo, and so the subject had to follow. In the third condition, we implemented the interactive agent, and so as a subject, you were in control, so you got the leader role. Whatever you do, the agent followed. So in that respect, we could manipulate the roles. Not going into detail, these are the results. It's a scale on self-other integration, so how much do you feel integrated with the agent. So when only watching, it's significantly lower than the two conditions. In this case, we didn't find an effect of the role, basically. Now here, just to show that you don't only use technologies to simulate what we can already do in the physical reality, but here we applied a body swap paradigm. So to tell it very shortly, what we did was to display the perspective of one person. We displayed that into the glasses of the other person. So when you were tapping together, you actually didn't see your own arm, but you saw the arm of the other. Right? So you swapped the body. And we were interested to see, does that increases spontaneous synchronization with another? And so basically what you do normally, you have a match between what you do and what you see. And you create a kind of mismatch. And so if you create a mismatch between what you do and what you see, you will alter your behavior in order to find the match again. I still have 2 minutes, so I will quickly go through this last, I think, interesting project. It's a collaboration with two theater groups, one in Denmark, Italy, the Odin Theatret, and another one in Brazil. And it's very physical theater, and so an important aspect of their practice is energetic training. So through training, try to explore and activate deeper levels of energetic qualities in your body and mind through body movements, exercises, and vocalizations. This is an example of such an exercise in our lab. So it's a bit of a... Normally they practice in completely different contexts, but this is, we had extensive capture of their exercises in our lab. And so through these movements, vocalizations, they try to find new energies in their level, in their body. Now the idea was, can we use interactive, immersive media to support these trainings? And the basic concept there was the concept of environmental constraints. And environmental constraints are elements, factors in the environment that define how you move. It's limits, forward movements, shape movement. And so the simple example of walking, you have to deal with a lot of constraints. So you have the gravity, you have resistances of the ground surface, you have objects. And depending on the constraints, you end up with completely different kinds of walking behaviors. And so the idea was, can we do that in extended reality? And so the idea was to create objects, elements in virtual reality that responded to users' actions, right? So in this case, you see algae, plants that could move in response to actions of a user. Now in design, you could decide the quality of this movement. So these algae could respond very quickly, very flexibly to the user's actions, or they could respond very rigidly. And so the main idea of experiments that we did was to see if we manipulate the quality of the response of this environment, could we transfer these qualities also to body movements, so to support this energetic training. So this was an experiment that we did. Time is limited, so I will not go into detail, but basically, again, we have support that if you change environmental constraints in VR, you could also translate these qualities into spontaneous body movements. And maybe a final slide to show that we do further research into how we can use these immersive technologies to create or make people aware about qualities and to stimulate them into their own bodies. With this, I would like to thank you, and I'm happy to take questions if there are any.
So we can take some questions for Professor Maes. Oh, you begin?
Thank you for a great presentation. In terms of biochemistry and neurosciences, the auditory biofeedback loop portion of your talk, could you speculate on, because audition goes perhaps through the amygdala, can you speculate on the levels of adrenocortical hormone levels in the blood and on endorphin levels in the brain?
All right. Well, then maybe I would refer to the Jimin, where sonification was used through these fitness machines. Well, of course, it needs further research, but the fact that the level of the feeling of exhaustion, of effort was significantly lower made us indeed think about what is maybe the biological effect underlying it. And so Tom did study endorphin levels, and there is something. So there is some thought about indeed it could change hormone levels that drive the effects that we saw in the study, at least. So yeah, it definitely is worth interesting to keep on studying this. Thanks.
Thank you. Now, a question on that side?
Please. I am Palestinian coming from Jordan. I would like to hear your comment on my subjective experience.
Yes.
I claim I can detect any motion behind a barrier in my mind and could measure in one measurement both the motion and momentum in one measurement in my mind, because the clock there out is in my mind. The classical and the quantum are both the same, out and in.
Yes.
And this is testable. I just see the clock here, the second hand, I say at 5, at number quarter, 30, anything, and I find it matching with the one in the outer world. Please, I would like to hear your precious comment. Thank you.
Yeah, first of all, I would like to see the test. I would like to do the test. I'm definitely not a specialist in quantum physics for sure. Yeah, I don't really know how to respond. Is there evidence of this?
It's something that has to do with consciousness and outer reality. Reality and consciousness. Any movement out is in. I check this with the clock and any other examples, but not necessarily now to tell more examples.
Well, typically,
if you are interested, you may ask me later, or anybody. You are all welcome. Thank you.
Okay, thank you.
Okay, question over on this side.
Thank you. Very interesting talk. There's a lot of questions I came to. The one that sticks with me, similar to the previous person here, in patients with Parkinson's, you mentioned stroke.
Yes.
There's a decrease in dopamine uptake as a feedback mechanism for the body and the mind. And the initial experiments you showed with the feedback of the music speeding up or like intentionally falling a little bit after the footfall.
Yes.
I would just imagine that being very frustrating to try and control something that's purposely desynchronizing.
Yes.
So have you looked into dopamine, the response of the body in feedback from the body to the mind?
Yes. All right. So dopamine is definitely a very important hormone, especially in relation to prediction. So there is quite a bit of research in music showing that synchronization requires anticipation and prediction. And so when this is successful, this gives a kind of pleasant experience, and it has been shown that this relates to the release of dopamine. And so in the relation, or in the context of Parkinson, we have done experiments with Parkinson's patients. And so they have if they walk, sometimes they freeze, right? And if you give them a metronome or music, the freezing is much less, right? And so it's thought that that aspect of prediction and dopamine release could be an explanation why the freezing is much less when you support the walking of Parkinson patients with music. So there is definitely relationships with dopamine and the symptoms of Parkinson.
And is your job someone who researches that, or you just provide the experimental technology?
Sorry?
Do you research those types of chemicals in the brain, or do you just do the technology? And
No, we don't do the substance, well, the hormone release we cannot study.
do you provide the mechanisms so people can research it?
We do the behavioral experiments, but there it stops for us. Yeah.
Thank you.
Another question? There is no one on this side, so a question on this side again?
Yes, I want to ask you if you've worked with professional athletes on this, because I know in the 1980s we did it, but not with music. We did it with tactile stimulus,
Yes.
and really changed ball scores and performance on both baseball and soccer, and hockey too.
Yes.
So, but hadn't tried music. So I was just wondering if you've tried it with professional.
Yes. Yes. So yeah, it's an interesting question. So for example, the D-jogger application where we want to alter cadence. So I showed general results, but if you zoom in into the results, you see that there are two types of people. Basically, you have responders and non-responders. And so some people just don't respond in any ways. They just do what they do, and they kind of seem to ignore the music. But then you have the responders who are very sensitive to. And if you relate it to professional versus recreational runners, we see that professional runners are more non-responders. And so we think, and we see it systematically throughout the series of studies that we do, and we think, and we asked also, and they seem to be more concentrated on their body and on the control of their body, and they seem to shut off from external stimuli. That is one possible explanation why these sonification tools are less useful for professional athletes.
Yeah, but therefore more for novices.
Yes. Yeah.
Okay.
So we have time for one more question.
Thank you for this really wonderful and fascinating talk. It seems like a lot of your research is geared towards therapeutic uses of music. I'm curious, A, are you a musician, and B, have you or are you aware of studies that are done in musicians, not from a therapeutic standpoint, but to explore perhaps the relationship between the musical frame of mind and, say, a meditative frame of mind?
Meditative. Yeah, well, I can say I am a musician, but definitely not a professional musician. If you relate it to sonification in therapeutic contexts, actually I started my PhD because I was a bit disappointed as a musician in the controllers that we had for manipulating digital sound. You have the sliders, but it's a very arbitrary mapping between what you do and what you hear. So I was interested in building more expressive controllers that really translate the qualities, what you do, into sound. And that, for me at least, led into these more therapeutic uses of music. You also talked about meditative aspects?
Meditative aspects of what goes on in a mind when a musician is in say, a flow state of performance.
Yeah, so we are definitely interested in meditative practices. So we build a small lab specifically to study meditation, relaxation, altered states of consciousness. And there we work further on the breathing application. And so where we connect physiology, breathing, especially heart rate, we capture that and then we translate this into audiovisual 3D world, let's say, and dynamics in this world. And so we try, but that's research for the future, to see whether that can support or improve meditative practices.
Thank you.
Yeah. Welcome.
With that, we can thank our speaker. The next speaker is also involved with a special event this morning. Professor Jerome Busemeyer, a distinguished professor at Indiana University, a long and distinguished career, more than 100 articles published, 4 books, fellow of the American Association for the Advancement of Science, fellow of the American Academy of Arts and Sciences, and the Society for Mind Matter Research has decided to award our Mind Matter Prize to Professor Busemeyer. And I'd like to read the certification. We do have a little memento. It says, the prize is awarded in recognition of Professor Busemeyer's seminal work, both theoretical and empirical, in the field of decision making. A particularly innovative section of his research has been the application of quantum principles to cognitive phenomena, or what is sometimes called quantum cognition. The underlying equivalence of the mathematics of quantum physics and that of the cognitive science indicates an intriguing link between the physical and mental domains of reality, which of course is what the society is primarily interested in. Professor Busemeyer's influential work combines profound depth of thought, and a striking sense for new and game-changing ideas in a truly exemplary way. So anyway, I want to congratulate Professor Busemeyer for the award and present him to give his talk this morning. What do quantum cognition, quantum consciousness, and quantum brains have to do with each other? Thank you.
Well, thank you, Bill. I'd like to thank Bill and Harold and the Society of Mind and Matter, and I'm honored to receive this award. And I'd like to thank Stuart and for inviting me here today, and Abby M. for organizing things. So I'm happy to speak to you today. Well, so let me begin. So the title of my talk pretty much tells you what I'm going to talk about. What do quantum cognition and quantum consciousness and quantum brains have to do with each other? So let me begin by saying, quantum theory is about a century old, and its reach has been vast and vigorous, spreading across various fields of science, even outside of physics, including the brain and consciousness and cognition. And so that's what we're going to deal with today. So, like I said, I'm going to talk about these 3 topics and also try to connect them all together again. So let's begin with quantum consciousness. And let's begin with the problem that generated the topic of quantum consciousness, the quantum measurement problem. So many people are familiar with the Schrödinger cat paradox by Schrödinger. And so the basic idea is, of course, you have this atom that's located in this box here that could be decaying or not decaying. And so this atom starts out in this superposition state that it's either decayed or not decayed. So there's some potential that it'll decay, and there's some potential that it won't decay. However, the atom then becomes entangled through a unitary operator with the equipment that's measuring the detection of the photon. And then this cat is sitting in this box with this apparatus that's doing the measurement, and the cat gets entangled with the apparatus and the atom that's going to be decaying. And so you're in this paradox where quantum physics says, well, we've got this superposition state. So the perspective from the quantum physics is we have this cat in a superposition state. And so that's the paradox. Now, well, that's not quite the paradox yet, because when we do our measurement, and then when we look at our measurement, we only see one outcome. We just see the cat, maybe the atom decays and the cat's dead. So why is it that humans can't experience this macro entangled superposition state? Why do we just see one of the outcomes? I mean, that's the puzzle. That's the measurement problem, fundamental measurement problem in physics. Now, how is this related to consciousness? I was reading a book by Stanislas Dehaene, and he was discussing his global network workspace theory in his book, Consciousness in the Brain. And he pointed out something very similar problem, a very similar problem occurs in studying consciousness. So he points out, according to quantum theory, the very act of a physical measurement forces the probabilities to collapse to a single discrete measure. In our brain, something very similar happens. The very act of consciously attending to an object causes the object to collapse the probability distribution of its various interpretations and let us perceive only one of them. So he was arguing that conscious acts as a discrete measurement device that grants up a single glimpse of the vast underlying sea of unconscious computations. So there seems to be this connection then between this quantum measurement problem in physics and the collapse problem in the consciousness. So anyway, so this collapse problem generated some theories about the role of consciousness in quantum physics. And so this started back in the 1930s with von Neumann and later by Wigner. And there's a picture of von Neumann on the left and Wigner on the right. So both of them argued that, a little jumping ahead here. Let's just give. Both of them argued that the system and the measurement device are quantum mechanical, and they become entangled in the superposition state. But consciousness is outside of physics, and so consciousness is what collapses the superposition state to an observation. Now, Stapp in the 1990s argued even a little bit further. There's a picture of Stapp, Henry Stapp. And he argued that our conscious free choice of an experiment actually changes what we observe in the physical world. So what we do observe is determined by what we choose to observe. So we have this kind of causal relationship here where our conscious choice of an experiment determines our conscious experience that causes this collapse that produces the observed values. So that's the how consciousness entered into quantum theory. Now, more recently, well, maybe after that, Bowman-Hiley, of course, discussed consciousness and mind and matter. And Pavo, earlier this week, provided a nice overview of Bowman-Hiley's theory, so I'm not going to go into the details on that. But basically, the Bowman-Hiley theory postulates this implicate order that then generates a physical aspect and a mental aspect. This is also related to dual aspect theory that Harold Ottmansbacher talks about. So those are the theories from concerning consciousness that arose by physicists. So that's the quantum consciousness part of this talk. So let's turn to the quantum brains part. Now, the quantum brain theories have a problem too. So we have the quantum measurement problem in physics, but we have a problem with the quantum brains, which is the decoherence problem. So what's the decoherence problem? So, what we require for interesting computations like in quantum computing is a superposition state, an entangled superposition state. But in order to maintain this coherent superposition state, we need an isolated environment. But the brain is this wet, noisy environment, and so it can rapidly decohere into one of our classical states. And so how can the brain be doing, useful quantum computations if we have this rapid decoherence? And so that's the decoherence problem for quantum brains. Well, this decoherence might be too fast for quantum computation. So let's take a look at some quantum brain theories across the years. One of the earliest was proposed by Ricciardi and Umezawa, and later was discussed by Karl Pribram and Jibu and Yasu and Viciello and Freeman. There's a picture of, I don't have a picture of Umezawa, but there's a picture of Karl Pribram. Yeah, so what they proposed was they wanted to use quantum field theory to describe classical brain states, like electrophysiological states, and they had a particular emphasis on modeling memory in the brain. And they argued that quantum field theory describes emergence of classical brain activity. A little bit later, Beck and Eccles proposed a more direct kind of relationship between quantum physics and the brain. So they propose that quantum mechanics plays an important role in brain processes by information transfer at the synaptic cleft. The mental states, so they had a dualistic theory, so that the mental states influence the quantum states to momentarily increase probability of release in transmitters at the presynaptic levels. Now, but even more recently than that, we have of course, everybody is familiar with this theory here. We have the quantum brain theories by Penrose and Hameroff. There's Roger Penrose on the left and Stewart on the right. And so what Penrose originally proposed was that elementary acts of consciousness are non-algorithmic. They can't be computed. Instead, they are gravitation-induced reductions of coherent superposition states. Now, at the beginning, Penrose didn't really know how to maintain this superposition state in the brain that's wet and noisy, and that's where Stewart came in and wrote to Penrose and collaborated with him and told him about the microtubules. And the microtubules could maintain the superposition state for extended periods, long enough periods of time to do some interesting cognitive computations before the collapse occurs. So in this theory, we have a reversal of the causal direction, so the quantum collapse then causes the conscious experience. Now, even after Penrose, Matthew Fisher, more recently, here's a picture of Matthew Fisher. He's a physicist at University of California, Santa Barbara. He was studying lithium. But anyway, he discovered that there's these Posner molecules in the presynaptic neurons that contain phosphate ions that could serve as entangled qubits. And these Posner molecules, they protect their coherent states against decoherence for very long ranges of times. Let's go back to the Hameroff theory. They were proposing that the microtubules could maintain coherence for like maybe 25 milliseconds, which is kind of fast for quantum computations, but not totally unrealistic. But Fisher was proposing to pose the molecules that could maintain coherence for much longer time, like hours or even days. Okay, so that's the quantum consciousness, that's the quantum brains, and now let's turn to quantum cognition, which is really my field. So what is quantum cognition? Now, first of all, before I tell you about quantum cognition, we also have a problem, and that's called the self-measurement problem. So, like, humans can do self-measurements, and measurement's an important part of our quantum cognition theory. But since they can do self-measurements, we're not really in control. We can't control these self-measurements. So in a real-life example, when you're going fishing, you decide when to pull up your fishing rod when you feel like you've got a fish hooked on the line. Or like in a laboratory that we'll talk about, like when you're staring at a Necker cube like this, and you see the Necker cube flipping on you, we have to ask you, when do you see the cube flipping? So you're doing self-measurements determining, well, I saw it flip it's pointing down to the left, or now it's pointing up to the right. And so you're doing self-measurements on this perception of this cube. So when do these self-measurements occur? Well, anyway, that's the problem that we have to deal with in quantum cognition. So we'll come back to that in a minute. But let's first just introduce quantum cognition. Now, when we work with quantum cognition, we're working with the mathematical basis of quantum theory and applying it to human decision-making behavior. And so why did we get interested in the mathematics of quantum theory for human decision-making behavior? So quantum theory, the quantum physicists in the 1920s, maybe they didn't realize it at first, but they actually invented a whole new probability theory. So we actually have at least two probability theories out there. One is the classical older theory that was axiomatized by Kolmogorov in the 1930s. But then the other one is the newer quantum probability theory that was axiomatized by von Neumann, also in the 1930s, actually. So these theories are two general probability theories, but they're based upon different axioms. So I don't want to go into too much of the details, but the essential difference between these theories is that in the Kolmogorov classical theory, events like, me forgetting a name of a theorist in this talk, an event, what happens when you get older. An event that happens in the world is represented by a subset of possible things that can happen. So an event, like in this figure here on the left, an event is a subset of points represented by the red circle. Or another event is the blue circle. So those are two events, it's subsets. So in Kolmogorov theory, we're working with a logic based upon subsets. And the logic of subsets is a Boolean logic. It's a very strict logic, actually. So it has axioms like commutativity and distributivity. Whereas in quantum theory, instead of representing our events as subsets of a sample space, we represent the events as subspaces of a vector space. And so quantum theory is placed in a vector space called the Hilbert space, and events are subspaces. So like in this picture here, the event F is this plane in this three-dimensional space, and the event, let's call it BT, is this other plane that's oblique with respect to the event F. Now, in classical theory, we have a probability function that assigns probabilities to the events. In quantum theory, we have a state vector that's a unit length vector that's sitting in the vector state, and we use that state vector to assign probabilities to the events. And so the way it works in quantum theory is we take our state vector representing the state of the system, and we project it onto the subspace representing the event, and we get the squared length of that projection to get the probability. And so one of the things that happens in these theories is that the classical theory, since it's using these subsets, obeys the Boolean axioms. It's a commutative probability theory. Whereas quantum theory, because we're using these subspaces, which are mathematically represented by, let's say, matrices, and these matrices don't commute. The product of the matrices depends on, the result of the product depends on the order. So it's non-commutative. And so it's this non-commutative feature that's critical for us to select, become interested in quantum theory, because human reasoning also has this non-commutative property. The order that we answer questions matters to us. So the first question can color how you're thinking about the next question, and so we get these kind of order effects that are important. So let's take an example application. We have many, many examples. Let's take one important example. It's called the conjunction fallacy. So this was actually originally discovered by Tversky and Kahneman, and is mentioned earlier in this talk today by Alan. Danny Kahneman won the Nobel Prize. Tversky would have won it with him, but he died too early. So this was work they did in 1983. So here's the problem. Now first, this is just one example problem. There's many, many examples like this. Now people don't always make this conjunction fallacy, but there's many example problems like this. So you could pick on this problem, but we have other examples. Anyway, so you told a story. Basically, you told a story about a woman named Linda. So Linda went to UC Berkeley, and she graduated from Berkeley in philosophy. And she was also active in the social movements. And so that's some prior information that you're given. And so then you're asked some questions about Linda, after she graduated. So you're asked, well, which event is more likely? How likely is it Linda's a bank teller? Well, when you hear the story about Linda being a philosophy major at Berkeley, bank teller doesn't make much sense. So you give it a low probability. Let's say you give it, often people give it a probability maybe like 0.2, low probability. Then they're asked, well, what about this? What's the probability that Linda's a feminist and she's a bank teller? Well, suddenly that conjunction sounds a little bit more plausible to people, intuitive to people. And so people will often rate the probability that she's a feminist and a bank teller higher, like 0.3. So now, this is called a fallacy according to classical probability theory, because this can't happen, because the event bank teller is this blue set of points, and the event feminist bank teller is the intersection of the red and the blue, and we're assigning a probability measure to this intersection. It's got to be smaller than the blue circle. And so we can never get a probability for the intersection to be higher than the probability for the single event. But this can happen in quantum theory, because let's say in this figure here, so you hear the story about Linda. This produces your state vector in this space, and the subspace represents the feminine event, and it's close to your state vector because the story matches the feminist event. But this bank teller event is far away from your state vector. Now, if we project from your state vector directly down on the bank teller, we get a really small probability from our quantum model. But if we first project on the feminist and then we project on the Bank-Taylor to get the sequence, we get a higher projection. So we can produce these kinds of conjunction fallacies naturally from using these, this Hilbert space and subspaces as our projectors. Let me catch up here a little bit. Yeah, so we developed a theory for probability judgment errors. This is just one example. And the mathematics is just here. I mean, and let me just go through this very quickly just to show you that how this works more carefully. So here's our probability Bank-Taylor. Here's our state vector. Can everybody see this pointer okay? I hope. Anyway, here's our state vector. You hear the story, Linda. You project onto the subspace for Bank-Taylor represented by this projector matrix, and you get the squared length. We can stick the identity operator in between and break that down into two parts. That's the projection for the feminist subspace and a projection for the non-feminist subspace. And when we distribute this thing through, we get this state right here. The state, before you take the squared magnitude of it, that state right there, that's our superposition state. And so the basic idea in quantum cognition is, well, when you're asked about Bank-Taylor, you remain unresolved about the feminist question. You don't have to make up your mind about feminism. You don't have to decide she is or is not. You're superposed. And so this superposition state, when you take the squared magnitude, you get the squared magnitude of the first part, that's here. You get the squared magnitude of the second part, that's right here. And then you get the cross product term, that's the interference term. And that interference term, if it's negative, it can produce our conjunction fallacy. Of course, this is a post hoc explanation for the conjunction fallacy, but then we can use the same theory to make many other predictions, like in particular about order effects. The order that you ask these questions can make a difference. So let me go on now to another point that's important for our talk. So we also use the dynamics, quantum dynamics. So I don't want to spend as much time on the quantum dynamics as I was spending on the quantum probability, but the dynamics are also quite different between classical and quantum. And let's just focus on these figures here to represent the essential difference in the ideas. So a common model that's used in cognitive science to represent the dynamics in a cognitive system is a Markov process. We use Markov processes like Markov random walks, Markov diffusion models, Markov Monte Carlo, Markov chains for modeling cognitive processes. Now, the essential idea of a Markov process is shown on this left-hand side. So imagine that you're watching a movie, it's a mystery movie, and you're trying to decide if a suspect is guilty or not. And so over time, you're watching the movie and you're collecting evidence. In a Markov model, your belief state is a point. It's well located. And so at any point in time, you're precisely located. Now, it may move around as you're watching the story, but at any moment in time, you're located, and so you're producing a trajectory. So this is your classic stochastic trajectory produced by a Markov model. A quantum model is quite different. So in the quantum model, the idea is that when you're not being measured, you're superposed. So at any point in time, you're kind of spread out. Your beliefs are kind of spread out. You have some potential to think the person is guilty, and at the same time, you have some potential to think the person is not guilty. I mean, there might be a higher potential that you'll answer that they're guilty than not guilty, but it's kind of diffused and spread out. So you're superposed until you take a measurement. And then when you measure it, you collapse on a point. So in the Markov model, when you ask for the measurement, you're just recording in a state that already existed. But in a quantum model, you're creating a state that didn't exist by the measurement. So this measurement becomes quite important for our theory. That's this non-unitary process that produces the collapse. So let me take an application of our quantum model. This is like a two-slit up on this figure right here. This is like a two-slit version of the cognitive two-slit version experiment. So it's a cognitive psychology two-slit version experiment. So in this experiment, it's what we call a dot motion experiment. You're watching these dots jiggling around. And it's a popular kind of paradigm for neuroscience and cognitive science because you can control the evidence. But you're watching these dots jiggling around, and there's a tendency for the dots to jiggle in one direction, let's say, or another. So you might have a tendency to jiggle mostly to the right, or they'll say jiggle randomly. And your job is to choose, well, are the dots jiggling to the left or to the right? And so you're collecting this evidence while you're watching these dots jiggling around. So we have two tracks, and so we're trying to simulate in a cognitive study, something like a two-slit experiment. This upper track is like when we're measuring which hole you go through. And this bottom track is like when we don't measure you. So in this top track, you're watching the dots jiggle around, and then we ask you to make a firm decision. What do you think? Are they, at this point in time, are they moving left or right? And then they wiggle around for a longer period of time. You're watching them. And then we ask you for a rating. Well, what's the probability now that they're moving to the right? So that's the one condition. So we measure which hole you go through right here, and then we measure your detector on your probability screen right here. In this bottom condition, we're watching the dots jiggle around, and we don't ask for any choice. We do ask you to push a button pre-planned ahead of time, just so we control for the motor movement. But there's no decision being made here. So here, we don't get to see, what hole you went through. And then you watch the dots jiggle around, you continue watching the dots.
I don't understand. Siri, so we have
Sorry,
two tracks in.
stop.
And so we are trying
Siri,
to
stop.
simulate in the cognitive study something like a
That was planned. No, you're watching the dots jiggle. I got to be careful how I say this. You're watching the dots jiggle around, but you're still superposed all this time. We don't get to see what hole you went through. Now, the critical thing is to compare Markov models to quantum models is to look at the distribution of ratings here, just like in a quantum two-hole experiment. In the slit experiment, we get your distribution of detectors across the screen. In the cognitive experiment, we get your distribution of ratings across a probability rating. And now, of course, if you in the case where we watched you, if you chose the right, we'll get a pile of distribution of probabilities on the right. If you chose the left, we'll get a pile of distributions on the left. But what we're going to be interested in is ignoring the choice you made. So let's just look at the marginal distribution that piles up, ignoring the choice. And we compare that to the case where you don't make a choice. So we're comparing a distribution of ratings when you made the choice, ignoring the choice, to a distribution of ratings when you didn't make the choice. And so the Markov model says, well, when you made the choice, you're just recording that something existed. It doesn't disturb the system. And so what the Markov model is going to predict, if you go through the mathematics, it obeys something called the Chapman-Kolmogorov equation, which is like a law of total probability. The Markov model predicts that choice here has no effect at all on the marginal distribution. So the marginal distribution when you make a choice is the same when you don't make the choice. But the quantum model predicts that making these choices moves you out of this superposition state, and then you collapse on the side, let's say, favoring the right. So you're getting this collapse disturbance problem. And so we predict an interference effect. So we predict the difference between the two. Oops. Went the wrong direction. And so what do we get? And this is a complicated figure. I don't want to spend that much time on it. But here on the horizontal axis, we have our probability ratings. Now, this is one subject. We do this for individual subjects. This is one subject, and I have to say, this was a really nice subject. Now, not all the subjects looked this well. But we did find a consistent effect across all the subjects. But this is a particularly good subject for the point we want to make. So this horizontal axis is a probability scale, and the vertical axis is relative frequency. And so this is a distribution that you, across many trials, that the subject hit these probability points. And what you can see at the upper panel is when they made a choice, and it's the marginal distribution following a choice. And the bottom panel is when there's no choice. And the first thing you can see is the blue line here is the actual data. And so what you can see is that we're getting a big effect, an interference effect of the choice compared to the no choice. And you can also kind of see some kind of a wavy pattern here that you see when you get these kind of interference effects in your two-slit experiment. And so what we're finding here is we do get these interference effects in this kind of wavy pattern that you might expect from quantum dynamics. Now, what are some connections? So these connections were made by my colleagues, Krennikov, Tsuchiya, Bruza, and Yamada, and Pathos. So where's the brain in quantum cognition? Actually, Stewart has made some remarks in some of his papers that he wrote, trying to connect his quantum brain to our quantum cognition. And so he's argued that, well, he could implement physically in the brain our quantum cognition using his microtubules. And so the microtubules, these can produce quantum channels, and you could have like concepts like happy or unhappy and job and no job they could be in superposition states in these microtubules, and when the superposition reaches some gravitational level, a collapse will occur, and you'll get the quantum consciousness of an experience that you're happy. You come out of the superposition state of happy and unhappy into happy. So he was arguing that we could model our quantum cognition models in his microtubules. Now, in his model, then, these our self-measurement would be happening every 25 milliseconds, which is really fast, much faster than we're modeling when we built our models. Also, we'd have to revise the mathematics in our model. Right now, we're not using qubits in our models to represent our states, and so we'd have to re-describe everything in terms of qubits. And we can't do that because actually we're starting to implement some of our quantum models on quantum computers, in which case we have to put them in terms of qubits. So that's one connection to the quantum brains. Now, Stuart also mentioned that we've always been agnostic. We're not committed to quantum brains, but it'd be great if the brain is a quantum computer. But Stuart often argues that, well, if the brain swims and looks and quacks like a quantum duck, then it probably is a quantum duck. Now, where's the consciousness in quantum cognition? So the consciousness appears when we talk about quantum measurement. So during unitary evolution, we assume this unitary evolution is unconscious. That's the unconscious processing, because this unitary evolution requires this basic rotation of your state vector in the space. Actually, Miller was talking about this with neurons. He had a high multidimensional neural state, and he was talking about the concepts being subspaces in this neural state, and your neural system can rotate these neural states. So we imagine that this this unitary evolution is the unconscious state, and when we request a measurement, like make a decision or give a probability rating, that's when you produce a conscious state. And so when we were doing our modeling, we actually fit mathematical models to the data. We actually are making the assumption that there's no self-measurements going on right here. The measurement only occurs when we request it. But with self-measurement, this could be an incorrect assumption in our model. So the self-measurement is a concern for us because we allow unitary evolution when we're not measuring you, but you could be doing these self-measurement collapses in here. So that's the problem of self-measurement. Now, here's another issue of self-measurement. In a Markov model, you're in a well-defined state. So when you're asked to do self-measurements, is the cube pointing down to the left or is the cube pointing up to the right? You're located someplace. So, when you reach this 0%, you say, okay, I'm in the 0%. I'm going to decide now it's pointing down to the left. But then you might move over across time and hit this upper state. Now you're going to change your mind and say the cube is pointing up to the right. But these decisions are based upon your location. So you decide, you're changing your mind whenever you're changing your location. Where in a quantum model, in a quantum model, you're not located anywhere. You're just diffused across the entire scale here. And so, this diffusion might be moving across time, and there might be a higher potential you're located one place versus the other, but you're not located someplace, so you can't say I'm located on the left or I'm located on the right. You have to do a self-measurement for that. And so what we have to propose in a situation when you're reporting by yourself, has the cube changed its location? Is it pointing down to the left or going up to the right? We have to propose that periodically you're doing self-measurements. Ottmansbacher actually worked on these problems and estimated these self-measurements, like in a Necker cube problem, should be occurring about every 70 milliseconds, which is a little bit slower than the Hameroff theory. Now, what can quantum cognition contribute to quantum consciousness? And this is where maybe we can contribute to the dynamical laws of consciousness. So if you have a classical theory of consciousness, a classical stream of consciousness, like for the Necker cube, then you have this, you're feeling you have this experience that's producing a trajectory across time. It's kind of classical trajectory. Now, if you have this classical trajectory, That's different from a quantum process. In a quantum stream of consciousness, you're going through measurements, self-measurements, where you're located. That's this dot in the screen. And then you're going periods where you're unitary evolution, and we're not conscious during this unitary evolution. So this is the picture that we would have in a stream of consciousness in a quantum model. So we can test these two ideas of stream of consciousness using what we call the test of the temporal Bell inequality. So the temporal Bell inequality, let me finish with this interesting, by the way, I missed a slide here. There's a little bit of a lag in, so this temporal Bell inequality was originally proposed for a test in physics, the test classical versus quantum dynamics in physics, but it was also extended to, the ideas were extended to cognitive science by Harold Ottmansbacher and his colleague Filk. Okay, so what is this temporal Bell experiment that we could do? So now this table here is a table illustrating the prediction of a classical model. So this is like a Bell inequality test, and so we're going to derive a prediction from that all the classical dynamics have to obey. Now on the left-hand side of this, these first three columns in this table represent states, classical states that you're going through. So if you're watching this Necker cube, you're passing through these states. So these are the hypothesized states of the system in a classical model. You could be in the up state at time t1, you could be in the up state at time t2, you could be up state in time t3, or you might be in the up state at time t1, in the down state at time t2, in the down state at time t3. And so these are hypothetical states that you're passing through, and on each trial, there's some probability that you're going to pass through one of these three states. So this joint probability table is a theoretical table according to the classical theory. According to the classical theory, there should be some joint distribution that you are positive all three states, or positive in the first two and negative at this third time point. And so these are the theoretical classical joint probabilities that you pass through these states. Now on the last three columns, these are experimental conditions for an experiment. So in an experiment, what we do, we ask people a question. Did you change from time 1 to time 2? Did the Necker cube change from time 1 to time 2? If you didn't change, we give you a 0. So like in condition 1, if you didn't change, so in this first row, according to classic theory, you didn't change from time 1 to time 2, so we give it a 0. But in this second row, you did change from time 1 to time 2, so we give it a 1. So this is asking, did you change from time 1 to time 2? And everywhere we got a 1, that means that would be a case where you had a trajectory that changed from time 1 to time 2. In the second column, we have all the cases where you change from time 2 to time 3. So we got a 1 right here, because from time 2 to time 3, you passed through a trajectory that changed from time 2 to time 3. And then in the third column, we have all the trajectories. We got a 1 for all the trajectories where you change from time 1 to time 3. So here we have a 1 here, because we changed from time 1 to time 3. And so the experiment is asking pairs of questions. Did you change from time 1 to time 2? Did you change from time 2 to time 3? Did you change from time 1 to time 3? And according to classic theory, you can derive mathematically, it's kind of easy, that all the classic theories, not just Markov theories, must predict that the probability that you change from time 1 to time 2 plus the probability that you change from time 2 to time 3 has to be greater than the probability that you change from time 1 to time 3. The reason why that's true is because this third column, every time you have a 1 in this third column, you also have a matching 1 in the first two columns. So the first two columns that are on the left-hand side of this equation, this inequality, cover the right-hand side of the inequality. And so all the classic theories must obey this. Now, we haven't done many experiments on this. In fact, there's only one been done. But the first experiment that we have done does support the quantum model. We get violations. The quantum model can produce violations of this temporal bell. And so it suggests that there's something more going on than classical dynamics. I'm running out of time, so I'm going to skip this page here. So I'm going to conclude. So the development of science cannot be determined solely by somebody's personal will. And when we're on the road of scientific research, we need to stop and think think for a while in order to have a clearer direction of our progress. And 100 years ago, when people were faced with some experimental results that were contrary to the laws of classical physics, scientists like Bohr and Heisenberg and Schrödinger and others, they pieced together quantum theory. Now the same is happening again in the realm of consciousness. Quantum theory might once again exert huge power. It provides a new perspective for people to comprehensively understand consciousness and judgment and decision making. And it may also herald the arrival of a scientific revolution. So that's where I'll stop today, and thank you for your attention. And I'd like to thank Harold and Major Liu for the comments on this talk.
Thank you. Great. So we have time for questions, if there are any. This gentleman over there.
Yes, it seems to me that we in the audience, the brains of us in the audience, have to maintain a superposition state between a presentation of consciousness, such as yours, and the first speaker this morning, Dr. Schurger. In other words, is the squirrel in our head dead or alive?
Yeah.
How do we collapse that waveform function?
Yeah.
Do you have any advice?
Well, I think we have to, like the first speaker said, we have to have experimental tests of these theories. And so when we start doing more rigorous experimental tests, that's when we're going to start resolving our indeterminism. So, but like this test, for example, this temporal Bell inequality or other Bell inequality tests in cognition tend to suggest that, well, there's some kind of, at least the mathematics of quantum theory is doing a better job than classical theory for explaining its behavior. And so then if we follow Stewart's argument, if it quacks like a duck and smells like a duck, maybe it is a duck. But I think the answer has to be we need stronger theoretical tests of these competing theories.
Yeah.
And something like the temporal bell is a way of, to get these kind of tests.
So it's
an empirical question still.
It's a dead duck or a live duck or a cat or a squirrel, and until then, we'll have to just kind of maintain this inner menagerie, I guess.
Yeah, you know, the problem too is you might collapse for a while and then go back by unitary evolution into uncertainty.
So wondering how you see this fitting into like a meta explanation of consciousness being more than just the measurement, but also this larger possibility. Then it gets collapsed into an awareness that we're arguing whether it's localized into the brain or if there's a meta and then it begins to be filtered and picked up by the brain.
Yeah. Well, I mean, yeah, I mean, if everything's unitary and there is no real collapse, then we're all in this big superposition together. And so in a way, that if we want to give up the real collapse idea and maintain unitary, then we're in this like multi-universe of superposition states, you know. And so, you know, we have to keep that as a tentative possibility, I suppose.
I won't take away the
Thank you for your talk. The bottle half empty or half full is a cognitive problem. Could you use, you know, quantum probability application because it offers vectors rather than me that always goes for the classical approach and I get absolutely flummoxed in state of static sets?
Yeah. Well, I mean, one nice thing about quantum theory maybe is that we can model both your classical behavior and quantum theory in a sense is a generalization of classical probability theory. Because classical probability theory is like you have your events are all commutative. But in quantum probability theory, you have commutative and non-commutative events. And so, you know, if you have a representation where all your events are commutative, you're putting all the events in the same sample space, basically. Or you're using one fixed basis to represent all the events. And so your judgments will then all be classical. But if you have another person who needs to change the basis of their thinking, so in other words, they use one basis to interpret events in one way, but then they have to change the basis, rotate to a new basis to interpret events, then they're going to be non-classical, and they'll have non-commutative results. So, and you can move from classical to non-classical. Let's say, you know, if somebody doesn't have a joint representation of the problem, a complete sample, single sample space for the problem, you could maybe show them that Venn diagram and encourage them to move into a classical space by the Venn diagram, and then they'll form a commutative space. Now, let me make one other point, though. A lot of times people ask me a question, well, why would evolution use quantum probabilities for judgments instead of classical? The reason why is if you have a classical probability, if you put everything in a commutative space, the space grows exponentially out of control. It's like if you have one question is binary, it's two outcomes. If you have two questions, it's 2 to the 4th. If you've got 3 questions, it's 2 to the 8th. It goes 2 to the n. And so Bayesian researchers have this problem of how do they deal with this exponentially growth in the probability space? And they often have to produce impose a lot of conditional independence on the system to do that. Well, quantum theory can do this reasoning, can reason about an infinite number of questions by rotating the basis. So you can stay in a finite dimensional space and just rotate the basis around to answer all kinds of questions. So there's a kind of a trade-off. So Mother Nature seems to have made this trade-off where, well, I can answer all kinds of questions by rotating the basis, but then the disadvantage is I'm going to get uncertainty properties and interference effects as a consequence. So that's a long answer to your question.
Thank you very much. Yes, please.
Yeah, thank you very much for making me see things differently here. But the question that comes to mind to me is, does this leave room for undeciding? So by deciding you make a measurement, it collapses. Is there any way to kind of get back to kind of the openness of before a decision was made?
Well, I mean, once you collapse, like I said, there's a unitary operator that can move you back into uncertainty. So if you're watching evidence, and so your friends say, well, what do you think, the person's guilty? You say, yeah, I think the person's guilty. Maybe you collapse. But then you're still watching evidence. That's going to move you again back into uncertainty. So you can move from certainty to uncertainty through the unitary evolution of the system. Does that answer your question?
It does, but now you're adding different vectors on. So there's a difference between that, if I understand things correctly, there's a difference between moving back into uncertainty after you have decided something than if you hadn't ever decided. Is that correct?
Yeah, I mean, well, it depends on where the unitary evolution might take you back to the original state you're in. It could blur it out, so that you become focused on one state, but because of the nature of the unitary evolution, it might blur you back out in a complete uncertainty again. So so it depends on the nature of the dynamics. So you could become completely uncertain over time about an issue.
Thank you.
Hi. Thank you very much for your talk. I've got a feeling that this might be a stupid question, so please forgive me if it is. In the experiment at the end with the Becker cube, the data that you had, the graph, there were 2 possible states, the 1 and the 0. When I look at the Becker cube, there seem to be 3 possible states, the third one just being a 2-dimensional series of overlapping squares. That doesn't feel like a superposition. It feels like a distinct third state in and of itself. How do you account for that in this more sort of binary switch?
I mean, it's like when you're staring at this Necker cube, right? And you see it. You can actually, when I stare at this Necker cube, I can actually see. Almost like I feel like I can. I think I see the superposition state a little bit. I mean, it goes through a period where it's kind of like in the process of flipping over in my perception. Is that what you're maybe talking about?
Not so much. It doesn't feel as if it's both at once, because it sort of loses the 3-dimensional quality altogether. It just looks like a 2-dimensional.
Oh, I see. I mean,
series of
I mean,
shapes.
of course, that would be. Yeah, that would be projecting So, you know, we might be projecting on a subspace that's representing as a three-dimensional, or we might be projecting on a subspace that's representing as two-dimensional. So there might be different subspaces that you could project to that would give you different perceptions or conscious experiences. So it's not like maybe in this Necker cube you're not really limited to a cube that's like pointing down or looking up to the left. You know, you might even have other conscious experiences. Each one of these conscious experiences might correspond to some subspace that you could project onto. So you can project onto a plane as well, image of a plane.
So, can I ask one extra?
Okay.
So if I was participating in that study and I was asked at a particular point whether I was in the 1 position or the 0 position, and my perception at that point was in this third modality, the two-dimensional representation, how would that be recorded?
Yeah. How would we model this in-between state?
Yeah.
I mean, yeah, that makes me wonder that, well, I mean, I don't have a model for it right now. And so I'm wondering if our model is not really correct, that the consciousness is not really limited to just measurement states, but maybe somehow we are conscious of the superposition state. I mean, I can kind of feel like I see some kind of a in-between state sometimes when I'm staring at this Necker cube. So it's like, or like when you're,
It feels more like a distinct
Okay,
state
well,
of itself.
let's move
Yeah.
on. One
Yeah.
last question.
well,
Pablo.
anyway, it might be that we're wrong about you're only conscious of the measurement. It might be that you can really feel the superposition state. That's a good question. I don't know. Yeah. Yes.
Yeah, thank you very much. I guess my question is related to these previous ones, but if I remember correctly, there was the idea that the unitary evolution would be unconscious, and then when there is a collapse, there is consciousness. But wouldn't it be also very natural to think that our typical stream of consciousness is the unitary evolution? So we are even conscious at that stage, and even then, if you take a very simple choice situation, you go to a restaurant, there are 3 things you might want to, 3 options that you're interested in, and you think for a while, and then if you like there's a collapse, you will choose one of them. But
Yeah. I mean, I think
can't we all be all conscious all the time of what is happening?
Yeah, I mean, that's a good question. I mean, we've been assuming in our work, and it might not be the right assumption. It may be that we have some conscious feeling for the superposition state as well, so that we are aware of the superposition state to some degree. I mean, there's different degrees of consciousness.
Mm-hmm.
I mean, maybe when you resolve your opinion, make up your mind, I like this restaurant better, then it becomes clearer. But before that, you're like you can feel yourself leaning. And so there is this, it may be that consciousness can even, to some level, pick up, these superposition states, I think. I mean, that's something new that we don't know yet, but that would be contrary to what we're thinking right now.
Thanks.
Yeah.
Okay, we should end there, and we'll reconvene at 11:20, and we should thank our speaker one last time.